Okay, so hello and welcome everyone to week 4 of interactive live sessions for the course called Fundamentals of Convective Heat Transfer. It's being offered by NPTEL and it's being taught by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras and I'm the TA for this course, and we shall be like every other week, we shall be solving some problems together and having open discussions about anything and everything related to this topic. So, all the lectures of week 4, if you have gone through them, involved the solutions of external fluid flows, or more specifically for boundary layers, both thermal as well as hydrodynamic boundary layers, and how the solutions of them turn out to be. So, without further ado, let's get started. So we'll start off with question number 1 of today's session, which is asking us that assuming a linear velocity profile that is given by u over u infinity equal to y over delta, and using approximate momentum integral method, find the expression for boundary layer thickness delta. Then four options are given, which include different expressions of delta. Option A says it's delta equal to 5.47 into x over root rex. The form is the same for all of them. That is delta equal to some constant into x over root rex. You have to find out what that constant is. That constant is different in the four different options. For option A, it's 5.47. Option B is 4.64. Option C is 3.47. And option D is 5. So in this question, you have to apply the approximate momentum integral method for flow over a flat plate and then try to solve for it. There is no hurry, take your time. Once you have solved, you can either unmute and answer, or you can type in your answer in the chat box. If you have any doubt or query regarding the question, you always feel free to ask. Okay, so we have one response in favor of option C. Let's see what others have to say. Okay, another in favor of option B, another C. 3.464, yeah, so that's C, yeah. Another option, response in favor of option C. Option B. Another response in favor of option B. So we have a split crowd, 50-50 in favor of options B and C. Okay, so let's take a look at the solution. The solution is option C. Uh, Delta equal to 3.47 into x over root rex. So how we go about solving is we use this approximate momentum integral. Sorry, we use this approximate momentum integral method, which is given by dou x of integral u over u infinity 1 minus u over u infinity 0 to delta into dy equal to tau at wall over rho u infinity square. Right. So now plug in the value of u over u infinity as y over delta. What we get is dou x of this is y delta and this is 1 minus y over delta. So this becomes integral of sorry, I'll use this here, I'll use this here. So y over delta minus y squared delta squared into dy. This gives us dou x of this becomes delta squared by 2 and delta squared by 2, yeah. So divided by delta is delta by 2 and this becomes delta cubed by 3. It gets divided by delta squared, so it's delta by 3. So ultimately we have uh, half minus 1/3 is 1 over 6, right? So 1/6 of dou delta d delta dx. This is what we have in the left hand side, and the right hand side we can write as uh, so tau w can be written as uh, tu ty, right, into mu. So this dou u dou I, since it's a you know so the picture is like this. So this is the boundary layer, and what we are telling is this velocity profile is linear with respect to y. This is y. So at y equal to delta, the value of u is u infinity. So the slope of this would be what? So this slope dou u dou I, this is actually constant across y. So this can be written as u infinity minus 0 divided by delta minus 0. So this is nothing but mu into u infinity over delta. Right? So we can simply replace this as mu into u infinity by delta, and here we have rho u infinity squared. So u infinity gets cancelled, and mu by rho becomes nu. So this is equal to I'll write it here. So this is equal to nu over delta u infinity. Right? Now this can be written as delta into dou delta equal to 6 mu over u infinity into dx, right? So now if I integrate, then this becomes delta squared over 2. So this is from 0 to delta, and, and this goes from 0 to x. These are all constants, these stay as it is. So this becomes 6 mu by u infinity into x. So I'm moving this here. So what I have is delta squared divided by x squared if I write. So then 2 goes up. This is 12 mu. I've taken u infinity. 1x I've taken extra on the denominator side here. So there will be another x over here. So basically ux by in ux by nu, this is nothing but 12 divided by re, right? Now if I take square root on both sides, delta over x becomes under root 12 over under root re with respect to x. So now delta I can write as, okay, so square root of 12, this turns out to be 4.3.47 approximately. And this x I'm pushing it up there, and this is under root rex. So this is my expression for delta, which matches with option C. I hope this is clear. Any questions regarding this one?
So this momentum integral method and von Karman method is that both same.
Sorry, I couldn't get you. Can you tell your question again? This is von Karman fundamental only, right?
Yes, this momentum integral method and von Karman integral method same.
Yeah, yeah, they're same. Just another additional term is for, the derivatives, u infinity along x-axis in the axial direction. That will appear only when there is a pressure gradient. Since this is a flat plate and there is no imposed pressure gradient, so that term would be zero. Otherwise, rest of it is the same. So instead of three terms, we are dropping one term. Otherwise, there would be an additional, u infinity du infinity dx kind of a term. Since this is zero, we are dropping that.
So, but actually the solution of that von Karman is 4.64 by root Rex.
Is it so? Anyway, I don't know that, but as far as this process is concerned, do you see any mistake anywhere? See, the main thing is what profile we are assuming. That would determine what would be this constant value. The functional form would be the same no matter what, but this velocity profile which we are assuming, that is important. So it could be 4.64 for some other profile. So wherever you saw that the von Karman integral method has that solution, uh, try to check which velocity profile they are assuming. That would be the important determinant over here.
So in that in my note actually u by u infinity is taken as 3 by 2 y by del minus 1 by 2 y by del cube.
See, so there a cubic profile is assumed. Assuming a linear profile.
Okay, sir.
That makes the difference. That's it. Otherwise, von Karman momentum integral and this momentum integral is exactly the same. This is von Karman momentum integral only.
So actually only we need to assume that parabolic profile.
Yeah, there is no way to accurately say that parabolic is the correct, cubic is the correct. Even a linear profile like this gives a good enough answer, right? So if you have gone through the lectures, you'll see that these are the approximate solutions, and there are proper analytical Blasius solutions as well. They have a very little error in between them, and there is so the overview is there is no one correct velocity profile which we can say that this is the correct one. We can make different assumptions. One assumption can be better than the other or worse than the other, but there is no one single correct answer to this. That which velocity profile is followed within a boundary layer.
So we'll be giving the given that velocity profile.
Yeah, the questions it will either be given or told that you have to assume something. So there, anything, any justified assumption would be correct.
Okay, sir. So but the Blasius equation we can take it as 5.
Yeah, for Blasius equation, it will come down to 5.
Okay, sir.
Exactly. So for 5 would be the answer if it was a Blasius solution. This is for a linear velocity profile. So I'm taking your word for it. If I take a cubic profile, maybe something, I'll get an answer like this. And then 5.47 for something else. I don't know. Maybe parabolic, maybe sine. Okay. Is the idea clear?
Yes, sir.
Yeah.
Sir, why not option B?
Why not option B? Because I already told in the question that you have to assume a linear profile, not a cubic one. Using a linear profile, this is the number that we end up at 3.47. If I had not used u by u infinity as y by delta and some cubic profile instead, then the numbers would be different, and finally this number we will end up at.
Okay, sir.
Okay. Any other questions?
So there is a correction. Actually, it is a square value. It's not cubic.
Square parabolic. Anyway,
Okay, sir.
so it's not a cubic but a parabolic. Is that
Yes,
okay?
sir.
So anyway, it doesn't matter whatever profile I take, and using this same set of calculations, we will end up at some number, and that number would sit before this x over root Rx, which is the functional form of how delta varies. Okay. Any other questions? Good. Okay. So we will move on. We'll move on to question number 2 of today's session, which is asking us that for boundary layer flows on shaped body, what is the condition for 2D stagnation flow? So we learned this Faulkner-Scan equations for flow over wedges, which have a certain angle, let's say pi beta. So there u infinity is equal to some c into x to the power m, right? So what is this m value for a 2D stagnation flow that you have to find? Okay, so we have one response in favor of half, or option B. Let's see what others have to say. Take your time, there's no hurry. Once you have figured out the solution, you can type it in the chat box. Okay, we have another response in favor of option D. Let's see what others have to say. Option B. Option D again. So for boundary layer flows on wedge-shaped body, what is the condition for 2D stagnation flow? We know that there is a relationship between M and beta, right? So once we figure out what beta is for a stagnation flow, then we can find it out. So what is a 2D stagnation flow? What does it basically mean? Alright, let's have a look at the solution. The solution is option D, m equal to 1. So what a 2D stagnation flow is, let's say if my free stream velocity is in this direction, in let's say x direction, this is x, this is y, then if I have a straight wall which is stopping the flow directly, so my right hand is, let's say, you can see my video, right? So let's say this is a wall like this, and the flow is coming this way and hitting it. So it can't push it, it will have to divert this way, but the velocity in the x direction is getting stagnated due to the wall. So that's why this is called a 2D stagnation flow. So you can imagine how the flow field would look like, right? So it would be something like this. Now this angle, this would be the wedge angle now, equal to pi beta. And what is the exact angle? It's a straight wall. So what would be the angle? Anyone? What would be this angle? It's a straight line. What is the angle between, two wedges?
180.
Huh?
180.
Sorry? 180 degree, right? Pi, basically.
Yes.
Right?
Yes, sir.
Yeah. Okay. And what is the relationship? So beta, the value of beta would be 1. So what is the relationship between beta and m? How can we write m in terms of beta?
Beta upon 2 minus beta.
Right. So if I just plug in this value of 1, this becomes 1 divided by 2 minus 1, which is equal to 1. So simple solution. Okay. Any questions regarding this? Clear, right? Okay. So we will move.
Sir, in case 3D flow,
Yeah.
in case of the 3D flow, what value of the EM?
See, for 3D flow, this kind of a formulation itself breaks down. So it would become something entirely different. That would be way more complicated than this, which is out of the scope of our discussion right now. So first of all, without considering 3D stagnation flow, let's say if I had a 3D wedge like this. So 3D wedge means this is something like a sphere. So this is, you can imagine, right? If I make something like this and rotate it, it would form a sphere or a pencil nib for that matter, pencil or a pen nib. And this is x, y, z, and I have some u infinity coming in. So, doing something similar, u infinity would be something like c into x to the power m, and here also we have some included wedge angle pi beta. There would be some functional form between m and beta, but I don't know what that exactly is. Maybe this is something you can look up. Okay.
So here in this question is asked about the wedge-shaped bodies, right? But the figure that you have drawn is actually plain or is
No,
both.
I'm telling that it's a 2D stagnation flow, right? So it's an extreme case of a wedge. So a wedge is like this. If I keep increasing the angle between it progressively, then it finally becomes something like this, a flat wall, which causes this 2D stagnation flow. Wedge shaped body, I am telling because we will use this formulation that m equal to beta by 2 minus beta. This comes from the theory of a flow over a wedge shaped body. Since we have to use this, that's why this piece of information is included. And you can understand, right? A wedge, if I keep on increasing the angle of it, it ultimately becomes a 2D stagnation flow. I can, do even more extremes and make this an obtuse angle like this. In that case, what would happen? The flow would, uh, so if I have a flow like this, the flow would converge like this, right? And this would be the included angle then, by beta. Beta would be greater than 1.
If the wedge angle is given, then corresponding to that beta will be changing, and we will be having different value for m.
Okay, so that's
Okay.
the gist of this kind of a problem. Any other questions? Okay, good. So we will keep moving on. We will move on to question number 3 of today's session. It is asking us what is the non-dimensional equation obtained from the below given energy equation. So this is a form of the energy equation that is given. So if I non-dimensionalize this, what form will I get? So there are three options given below. These are the non-dimensional forms of this energy equation. So which one would correctly represent this non-dimensionalized energy equation? Okay, so F over here comes from the Blasius type solution. So U over U infinity is equal to F prime, if you remember. This is what we have to use. Now I'm giving a hint over here, so you can try to fully non-dimensionalize this entire equation, simplify each term and try to see where that goes. Or there is a trick solution where you can, look for specific terms and see which equation matches with that. This is a hint that I'll drop. So the energy equation is given for a specific case which has, the uh, convective terms, the diffusive term, and the viscous dissipation term as well. So if I non-dimensionalize this entire equation, what kind of a form can I get? There are three options given here. You have to pick any one of them. Okay. Yeah. Hello, Mukesh bhai. Yeah. फ्लास्क एक मिला है लेकिन उसमें वो रिबन नहीं लगा है, मतलब आई हैव टू होल्ड इट एंड कैरी, तो उसके लिए और एक ढूंढ रहा हूँ. ओके. ओके, ऑसम. ओके. या प्लीज डू. प्लीज या थैंक्स. ओके. थैंक्स मैम. बाय. Any guesses what it could be? I'm not asking you to fully non-dimensionalize this right now. That would be very involved. But can you make a intelligent guess as to which one it can be? Just looking at the form of each terms in the dimensional form and as well as in the non-dimensional form. If you can relate a few terms, you can get a hint which of these equations would be the correct non-dimensional form. One hint I have already dropped. This equation u over u infinity is equal to f prime. You have to do something with this. Okay, so let's have a look at the solution. The solution is option C. Now, how to get there? As I said, that u over u infinity, this is equal to f prime, right? By definition. Now, if I now in this equation we have this viscous dissipation term, dou u dou y. So, okay, so first of all, where does f prime lie? F prime could be anywhere, you know, uh, both u and v would have f prime, so it could be any of these equations. Now, lastly, this dou u dou y whole square term. So for that, I need to first of all find out dou u dou y, right? So dou u dou y would be u infinity into dou f prime, sorry, dou f prime dou y. I can now f is a function of eta, so I can write this as dou f prime of dou eta into dou eta dou y. So anyway, forget about all the other terms. Dou u dou y is proportional to f double prime, right? This dou eta of f prime is f double prime. So and dou u dou y squared, this would be proportional to f double prime squared. So in these three equations, it's only this option C which has a f double prime squared term. You understand, right? So that's why option C would be the correct answer. And the rest of it, you are always welcome to fully non-dimensionalize this. The f's and f primes, they would simplify finally to give only a term containing f and not any f prime. And this theta double dot, this would come from this diffusion term, which has dou 2t dou y2. That would give us this theta double prime. And this term, the viscous dissipation term, that would have Eckert number and Prandtl number in front of it, and that doesn't matter. functionally it would depend on f double prime whole square, as we can estimate from here. So from a simple visual inspection, I can guess which one would be the correct answer. You understood the trick, right? Any questions regarding this?
How can I solve this?
So as I said, okay, so if you want to do this formally, then of course you have u over u infinity equal to f prime. Then dou u dou y you can find out like this. Similarly, there's an expression for v also, right? I forgot the expression. I'll have a quick look at it. So it's something like this. It's equal to half u infinity nu by x into eta f, sorry, eta f prime minus f. So v is something like this, and t you can t you can use this thing like t equal to theta into tw minus t infinity plus t infinity. So all these values of u, v, dou u, dou y, and t you plug in to this equation, and then you use the scalings, different scalings. So for u the scaling would be u infinity, then for t the scaling would be t infinity, like that. You get the gist, right? After using different scales, you can non-dimensionalize this to this form. It would be mathematically a bit involved. Okay, any other questions?
So actually, what is the necessity of this non-dimensionalizing this equation?
What? Sorry, I couldn't get your question.
I mean, why we are actually non-dimensionalizing it?
Good, very good question. Why do we do non-dimensionalization in the first place? So forget about all this. So let's take a very simple example. So um, so let's say I have a balloon like this. Sorry, I'll draw a bit better. So let's say I have a balloon like this, which is falling at a certain velocity v, and this velocity would depend on the diameter of this, then the mass of this thing, as well as gravity, right? There are many other things it might depend on. So this velocity would be a function of all this, g, m, d, and so on, right? You get the thing, right? So now uh, let's say I want to design this for the Mars rover, which is getting down on Mars. There's a balloon and all, and the atmosphere of Mars is different, everything, the gravity of Mars is different and everything, but I want to replicate the same thing in, let's say I'm doing the experiments here on Earth. So in order to relate those two different conditions, I have to maintain uh, what is known as similarity. So there are different aspects of similarity, like kinetic similarity, geometric similarity, and dynamic similarity. So to ensure all that, I can you know bring this down to some non-dimensional form, which is like, let's say, Reynolds number equal to some function of some other numbers. I'll call them pi 1, pi 2, and so on. So this is what we learned in Buckingham pi theorem. Now, once I get this form, it doesn't matter whether I'm doing the experiment here on Earth or on Mars. If I keep these non-dimensional numbers same, it would mean the exact same thing. So if I now come back to, let's say, heat transfer. So I have a 1 millimeter plate with some 2 millimeter per second square per second of flow going through it, and I have a, let's say, heat transfer rate Q dot of some 1 microwatt. Sorry, 1 microwatt per millimeter squared. Right. So this is one thing, and it could be scaled up to some 1 meter long uh, flat plate with, let's say, some 40 meter per second flow velocity. What would be the q dot over here if I'm asking that? How to relate these two? So if I keep the Prandtl number same, the Eckert number same, you understand, right? If I match those two, then from this experiment, I can find out what the value of this q dot would be over there.
So by matching means the same value.
Yeah, same values of what? Not q dot L, the values of Prandtl number and Eckert number, non-dimensional numbers involved in the problem. If I keep those same, then it would be exactly similar.
Okay, sir. So the value for the Prandtl number will be different for both condition, but
Yeah, so value of Prandtl number depends on what? Material property. So it could be if going over one situation and going over another situation like that. So then Prandtl numbers would be different. Prandtl number is a material property.
so like if we are using the Reynolds number, it's actually rho VD by mu, isn't it? So for both cases, the diameter and it will be different, isn't it? So
Yeah,
we will be having two different values of Reynolds number.
yeah, correct. This is a very good example. So let's say I have a pipe like this, which is of 1 millimeter, and I have some flow through it, let's say U, and ultimately I can use this Reynolds number equal to UD by nu, right? So
Yes.
get some velocity from this. Now I take a 1 meter diameter and I put some different, I match this Reynolds number. So if, let's say Reynolds number was 100 and this is also matching this Reynolds number to be 100. In that case, the velocity profile that I get here would be exactly the same as I got for the 1 millimeter pipe. There won't be any difference.
Okay, sir.
Get the
So
point, right? So if
this
I
similar same as that of prototype. I mean,
correct, exactly. So prototype and the
okay, sir.
so if the non-dimensional numbers I'm keeping same, the physics of the problem would be exactly the same. That's why it's preferred to non-dimensionalize every uh, equation that we can. Okay. Any other questions regarding this?
So one more thing is actually if we are actually doing a CFD analysis or anything for a bigger structure, if we make a prototype of that same structure in a smaller scale,
Mhm.
will the both the calculation will be same?
Yeah. So if you match the Reynolds number, then the flow behavior the same, even for the model as well as the prototype.
So actually, we can reduce the computation by
Absolutely.
bringing it to the prototype. I
Correct.
mean, if you're doing it in ANSYS or anything.
Correct. Correct. That is done. That is very frequently done in both industry as well as academic research.
Okay, sir.
Good. Okay, so we will now move on, if there are no more questions, to question number 4 of today's session, which is asking us now that we have to assume a cubic temperature profile, which someone cubic velocity profile is something that we were discussing earlier. Anyway, so for a flow over an isothermal flat plate. Now, applying the boundary conditions for boundary layer flows, express T in terms of delta T, Tw, the surface temperature of the plate, and T infinity, and Y. So finally, what would be this thing be? T minus TW by T infinity minus TWB. So there are four options given below. You have to pick out the correct one. Remember, it's an okay. So we already have a quick response option B. Okay. So the problem says it's a isothermal flat plate. So TW is a constant. It's not a function of X. Yeah, bro, you called? Hmm. Awesome. Thanks. Hmm. That's that shouldn't be a problem. वो रस्सी है ना? हाँ. Okay. Hmm. That's okay, man. That's fine. Okay, thanks a lot. हाँ हाँ. अभी वो मेरा वो NPTEL का सेशन चल रहा है यार, तो इसलिए I couldn't pick up your call. Okay, thanks man. Thanks a lot. Yeah, bye. Okay, so we have another response in favor of option B. One more. Let's see what everyone has to say. One more. B seems popular. So we have to assume that the temperature profile is cubic and then express T minus TW over T infinity minus TW as some function of y by delta t. What would that function be? There are four options given below. Let's pick the correct one. Some of us have selected option B and we are waiting for responses from others. Okay, so let's have a look at the solution. The solution is option B, so everyone picked correctly. The way to solve this is, you know, after assuming this velocity temperature profile, we have to use the boundary conditions that we know to find out these constants a0, a1, a2, and a3. So at y equal to 0, t is equal to tw, right? So this is my y, and we know that it's an isothermal plate. So t would be t wall at uh, at the so t would be equal to t wall at y equal to 0. Also, from the energy equation, if we write U dot E dot x plus V dot E dot y equal to alpha dou to T dou y squared, right, in a boundary layer. So at y equal to 0, U and V both are 0. So this gives me that dou to y, dou y2 at y equal to 0 has to be equal to 0 as well. So okay, so dou 2t dou y2 is also 0. So now using this, I'll now plug in this thing. So if I say that a0 plus, so if I put y equal to 0, then it's only a0. So a0 is equal to tw. This I am getting from the first boundary condition. From the second boundary condition, if I find out the second derivative of t with respect to y, then that would be, let's say, okay, so first of all, dou 2t dou y, this is equal to a1 plus 2a2y plus 3a3y squared, and the second derivative would be 2a2 plus 6a3y, right? So twice derived, yeah. So now I am telling that at y equal to 0, this value is 0. So 2a2 would be equal to 0, meaning a2 itself is also 0. Okay. Now comes the boundary condition at the edge of the boundary layer. So at y equal to delta t, I know that t equal to T infinity, which is the free stream velocity, free stream temperature, sorry. So now if I plug in whatever I know, so I know A0 is TW, so this will give me TW plus A1Y, so that is A1 delta T plus I got a2 equal to 0, so this term vanishes, and also I got a3 into delta t cube should be equal to t infinity, right? So this is what I'm getting as of now. I'll call this equation 3 and move on a bit. So I also know that at y equal to delta t, dou t dou y is 0. So the gradient of temperature becomes 0 at the boundary layer, edge of the boundary layer. So this I'll now use. A1 is equal to, okay, so A1 I don't know. A1 into delta t. A0 is TW, so TW plus A1 delta t plus, sorry, 2 A1. Let me do this correctly. So I have this equation of dou t dou y, right? A1 I don't know. A2 I've found out to be 0. A3 also I don't know. So it will be A1 plus 3A3 into delta t squared equal to 0. Am I doing this correctly? A1, this vanishes out. Okay, so I'll call this equation number 4. So equation 4 is A1 plus 3A3 into delta t squared is equal to 0. And equation 3 I'm writing a bit differently. So I'll divide it by delta t, the entire thing. So A1 plus it's A3 delta t squared. So that becomes, since I'm dividing by delta t, it becomes delta t squared. And on this side I have T infinity minus TW divided by delta T. Cool. So if I now take a difference between these two, these two would cancel out. I'll get 2 delta T squared A3 is equal to T W minus T infinity by delta T. Now I'll simply simplify this a bit. So delta T squared I'll send here. This becomes cube. 2 also I send it here. So this is the value of A3. Right. Now I'll put the value of A3 over here to find out A1. So A1 would be minus 3 delta T squared into A3, which is, I know now, T W minus T infinity by 2 delta T cubed. So delta T squared would cancel out. So this is A1 now. Now I'll put everything and assemble. So T is equal to A0, I know to be TW, plus A1, I have found out that it's plus 3 by 2 into T infinity minus TW. I'm taking care of the minus sign over here, mind it, divided by 2 delta T into Y, plus A2 I found out to be 0, and A3 is TW minus T infinity divided by 2 delta T cubed into Y cubed. Now if I simplify this, so I'll take this TW to this side, so it will become T minus TW, and I'll divide by T infinity minus TW. So I'll write this as T minus TW divided by T infinity minus TW. This would then become, wait a second, A1 okay, so it will be 3 by 2 y by delta t, and this would be minus half of y by delta t cubed. So this is the final form that I get, which is equal to option B. Makes sense, right? Sorry, I made a mistake here. This would be just 3. Okay. Any doubts regarding this? Any questions, anyone?
Any short trick for this question?
Sorry, what?
Sir, any short trick for this question?
I'm not getting your question. I'm sorry.
Sir, he is asking any short trick of this question.
Any short trick? No, you have to go through this entire painful process. Or you can simply remember this result because isothermal flat plate is a pretty common example. Okay, but otherwise, I don't know if there is any short trick to take care of this. This is a very painful problem. Okay,
Yes, sir.
okay, is there anything else? Otherwise, we will move on. Okay, so we move on to question number 5 now. Uh, this is also a very standard. Yeah. Okay, so
Please
question.
see question number 4 slide.
Do you have anything to ask regarding this? This is the question number 4.
Thank you, sir.
Okay. I'll be anyway sharing these slides with NPTEL. They will share it with you. Okay, so no need to blatantly copy. You can, and my handwriting and working out is also not a very pretty thing, but try to understand the process that we are going through. Okay.
Yes, sir.
Okay. So this is question number 5 of today's session. So this is also, as I was saying, a pretty standard case. So for flow over a flat plate with uniform surface heat flux condition. Earlier it was isothermal. Now it's uh, isoflux, you can say. Uh, it's shown in the figure as well. So assuming cubic velocity and cubic temperature profile, find the constant A for the expression given below. This is again very mathematically involved, so I would suggest you to remember certain results. So at least for isothermal and uniform heat flux, these are the two cases. Isothermal is this, and uniform heat flux is this. Okay, not zero. There will be constants. And we are assuming cubic profiles for both velocity as well as temperature. So doing all that, I'll finally get dou t over dou x equal to a into some functional form of Prandtl number, Reynolds number, and so and so. So what would be the value of this a? This particular thing was done in class, right? So I'll suggest you go back to those lecture notes. Doing this entire thing once again would be time taking. So cubic velocity profile would simplify down to something like what we did in the previous question. 3 by 2 y by delta minus half of y by delta cubed. Now a similar profile for theta, which is t minus t infinity by tw minus t infinity. This you have to find out for uniform heat flux. Previously, what we did was for isothermal condition. You have to do a similar thing for this uh, uniform heat flux condition. This case was done in class, right? So maybe while discussing, we can go back to the lecture slides. Try to find those.
So this quiz is not done in lecture.
Not done? Okay.
Yes, sir.
Okay, so for this, let's not waste much time because this is a bit difficult question. So I'll, share a different screen. Give me a moment. Yeah. So is my screen visible? I'll try to zoom in a little bit.
Yes, sir.
Yeah. So I'm showing the lecture notes from earlier. Uh, I'm not doing the entire thing. I'm cheating a little bit, but it's not cheating if we learn something. So we will go through the process of this one. So the question said that we have to assume third degree polynomials for both temperature as well as velocity. For velocity, it would be similar to what we did in the previous question, and we will get that 3 by 2 and half as the coefficients. Now, for the temperature, we have to first assume a uh, third degree polynomial like this. Uh, then using the boundary conditions. So this will be a different set of boundary conditions now. So y equal to 0 would be minus k into dou t dou y equal to q double prime. This is the heat flux. Since we have a constant heat flux, now I can say that dou t dou y would be minus of this q over k. And at the boundary layer, at the boundary layer edge, it would be similar things, t equal to t infinity and dou t dou y equal to 0. We know this. Then at y equal to 0, once again from the energy equation, we put u equal to 0 and v equal to 0 as shown in this right hand side. Then we will finally get dou t or the second derivative of t to be 0 as well. So plugging all those in, we will find the values of C1, C2, C3 and so on. And finally we will get something like this, where this thing, you can see this equation, right? The first one, T of xy is equal to T infinity plus this entire function of delta T and y multiplied by Q over K, right? So now we can further simplify this by taking a difference and dividing with tw minus t infinity and so on. So, okay, now this is the velocity profile, which I told that it would be similar to the previous problem. The boundary layer thickness is also given. This is also similar to the question. And the temperature profile is something like this, which we find out by putting in all the boundary conditions. Now comes the difficult part. Now we will do finally we will solve this energy integral equation, where both u as well as t has to be substituted, both of which are cubic functions. Now a bit simplified cubic functions, but anyway cubic functions. So So after plugging in the value of u as well as t, it becomes a product of 2 into 3 polynomials. So it becomes 6 polynomials. Then if we painstakingly solve for everything, finally we will get something like this, where this thing is 1 over 140. and we will assume that Prandtl number is greater than 1. So the thermal boundary layer would be greater than delta, and this dou x of dou t by uh, delta t by delta cubed, this would become equal to 10 into alpha over u infinity. Now finally, after solving for this integral, we will get something like 10 alpha over u infinity, and delta over delta x we already know from the question that it's under root 280 by 13 into 1 over root rex. Finally, plugging in all these values, we will get this delta t over x as something like this, where this number 10 into under root 280 by 13, that is the only number remaining. That becomes equal to 3.594, which was the A in our question. So I'll now change the sharing screen. Give me a moment. I'll stop presenting and share once again. Yeah, so my screen is visible, right? So finally, we get something like A equal to 10 multiplied by under root 280 by 13. And this turns out to be approximately 3.594. That's why option D would be the right answer. Okay. Any questions regarding this? The process became clear to everyone, right? So if we write down the steps, so first of all, u is a cubic function of uh, y. So this would be something like a0 plus a1y plus a2y squared plus a3y cubed. And similarly, the temperature profile would also be something like b0 plus b1y plus b2y squared plus b3y cubed. This is the first assumption. Then we use the boundary conditions to find out what the values of these ai and bi's would be. Okay, this is the second step. And in the third step, we use the energy integral equation. Which involves dou x of u into t minus t infinity dou y 0 to delta, and this is equal to, sorry, I forgot what it was equal to. Yeah, equal to this constant heat flux over mu rho Cp, which is the heat capacity of the fluid. So once we know u and t, using all this, we can find out what delta t would be in terms of delta t by x would be, and many other terms will be there. Prandtl number to the power 1/3, Reynolds number to the power half, and so on. 1 minus zeta over x to the power 1/3, and here we will have this number a, which in this case turns out to be 10 into under root 280 by 13. So if we had assumed a parabolic profile, this number would be different. If we assumed a linear profile, this number would be different. You get the point, right? But these are the sequence of steps that we have to go through. Any questions? Okay, so if there are no questions, we will move on. We'll move on to question number 6. This is a very simple question. So, what is the product of Reynolds number and Prandtl number called? Is it option A Stanton number, option B Peckley number, option C Grashof number, or option D Richardson number? This is the simplest question we have done so far in today's session. So what would it be? The product of Reynolds number and Prandtl number? Okay, we have someone telling it's a Peckley number. Let's see. Peckley number, Peckley number, Peckley number. Good. We will simply have a look at the solution. It is indeed Peckley number. Simple. Peckley number is defined in this way. Reynolds number into Prandtl number. Sorry. I'm sure there will be no questions regarding this one, but anyway, if you have anything, please don't hesitate to ask. Okay. Sorry. We will move on to the last question of today's session now. All sorts of boundary layer flows have similarity solutions. This is a statement. You have to say whether this statement is true or false. Okay, someone is saying it's true. Let's see what everyone else has to say. All sorts of boundary layer flows have similarity solutions. Is that true or is that false? False. Again, true. Again, true. Okay, so let's have a look at the solution. Solution is actually false. All sorts of boundary layer flows do not have similarity solutions. So we have looked at laminar boundary layer flows so far. They seem to have similarity solutions. In turbulent boundary layers also there is a form of a similarity solution. But there are a few special cases of boundary layer flows where they don't have a similarity solution. In what case it would be is, let's say if there is instead of a no penetration boundary condition, if there is some flow into the boundary layer, let's say there is a porous plate, so there are pores within this plate which allows some flow to come into it in addition to the free stream flow and boundary layer over it. There is some flow into it, so this is called a suction flow. Similarly, I can have flow addition as well. There could be flow very slowly but coming out of this boundary itself. So in that case, it adds momentum and the similarity solution argument does not work over there. There are a few actually engineering applications of these kinds of flows, suction flows and flow additions. Can anyone tell where? So in certain cases, over aerofoils like this, a suction flow is applied in order to prevent the separation of boundary layer. We will discuss this when we discuss separation. So a certain suction is applied so that the boundary layer does not separate. As a result, the you know the wake formation behind is suppressed, and as a result, it gets lesser drag and more lift. This is a very practical engineering application where this thing is used, and in this case similarity solution can't be applied. Clear? Am I making sense? Okay, so this was the last question of today's session. Thank you guys. So next week on so what's the date next week? Today is 29th, right? So sorry, today is 22nd. Okay, sorry. So today is 22nd. Next week is 29th. There won't be a class on 29th. I am traveling for a conference, so I won't be able to attend this. Instead, so I'm coming back on 1st September. So on 2nd September, we will have this session from 7 p.m. to 9 p.m. like usual. And the next day, I'm not sure what day that is, next Tuesday after 29th. So that is 5th September. 5th September again we will have class as usual. So please take note of this. You will be informed from the NPTEL team as well. On 29th there won't be any class. This would be shifted to 2nd September, and from 5th September onwards we will have the usual Tuesday routine that we have been following. So just there is this small change. Please take note of it. So today is week 4. We will discuss week 5 stuff on 2nd September and week 6 stuff on 5th September. Okay. Thanks guys. Good night.
Welcome, sir. Good night.
Good night, sir.
Thank you. Good night.